We're now going to return to one of the first ideas we talked about, and that's when we were talking about the traveling and the velocity and the idea of average velocity and instantaneous velocity. So we developed the idea of a derivative as rates of change. Now that you're familiar with limits, the door to calculus stands open. Limits are the fundamental idea, which then lead to the concept of a derivative and later the concept of an integral, which are both of the branches of calculus. First of all, we want to think of how we could define a tangent to a curve at point A, and one of the first times you probably heard of a tangent as when you were doing geometry and talking about a tangent line to a circle, and that was a line that intersected the circle at exactly one point. But as we're trying to define a tangent to any kind of a curve, not just a circle, you can see here that line L just intersects the curve at one point, but this is not a tangent to the curve, and line T intersects the curve at point P, but also it intersects the curve a second time, but this one is a tangent at point P. So it's not going to be some kind of a statement of just intersecting the curve once. So what is a tangent to a curve? As we look here at point P, this line is not tangent to the curve. This one is tangent to the curve, and it actually intersects the curve 3 times. This particular line also is tangent at the point P. So how are we going to define a tangent? Here it looks like it just touches the curve, but here it actually crosses the curve. Well, first let's get a sense of a tangent. A tangent gives a direction of motion. You may think of this as if you were riding along a roller coaster and you had a headlight on the roller coaster, and this tangent would essentially be the direction that this headlight was pointing. So here we are riding along the curve, and this is the tangent to the curve at this point. As this point moves along, then you can see how this tangent, or sort of the trajectory or line of motion, changes. So remember, we have 2 kinds of lines. A secant line is a line that would join 2 points on the curve, and a tangent line is what we're looking to try and define. We are just looking at a particular point. We'll call that point P when we're talking about the tangent line. So let's look so we get an idea of how we might define this tangent to the curve. So let's go ahead and look at the curve x squared, and this actually has the P and Q backwards to kind of what I had them and how we will see them, but we're going to be moving this P closer and closer to Q, and Q is actually our point of tangency that we're interested in. So right now we're looking at a secant line that joins up P and Q, and the distance from the x value at Q and the x value at P is h. And we can see the slope of this secant line is 7, and our h right now, that distance along the x from P to Q, is 3. We could move this point closer to Q. Notice my h is becoming smaller and smaller. We could make the h, this h is about 2 now, and we can see the slope of this secant line is getting closer to and approaching the slope of this tangent line. We could continue to make h smaller and smaller and smaller, and we see as we do that this secant line is approaching the tangent line, and in fact now my h is a little over a third, and my slope of the secant line looks like it's 4.36. As we get smaller and smaller and smaller, here's a point where h is extremely small. We're very close to the tangent line now, but we could still compute the slope because we're sitting at a point that is slightly to the right of Q, and we see that our secant slope is just a little over 4. So we could make a good estimate of our slope of our tangent line being 4. So our idea to define our tangent line at point, these are the P and Q are turned around from that demo, at point P would be to find the slope of the secant line PQ and then move Q closer and closer and closer to P. So let's go ahead and develop that idea and see if we can come up with a formula for this. So essentially our point, we're interested in finding our tangent line here labeled T, and that's going to be at an x value of a, so our function value is going to be f of a. and we will pick a point to the right of that, a plus h, and so that's h away from a, and so our x value at point Q is a plus h, and we'll just have a function f of a plus h then. So if we're looking at the slope of this secant line, we can see that our change in y is f of a plus h minus f of a, and our change in x is going to be a plus h minus a, which is going to be h. And so we could write the slope of this line, the change in y over the change in x. And so this is just our y2 minus y1 over x2 minus x1, and this is what we would get for the slope of the secant line. And now the slope of the tangent line is going to be the limit as h goes to 0. We get these h's smaller and smaller and smaller, and if we take the limit as h approaches 0, then these slopes of these secant lines would approach the slope of the tangent line. So this is going to be a very important formula. It's also often called the difference quotient, and when we have the limit as h goes to 0, then we do have the slope of this tangent line. Now remember that when we computed this difference quotient, that gave us the slope of a secant line, and that was the average rate of change of something. This one was the graphic we used when we were talking about the velocities traveling from Evanston to Rollins. Now, if we take the limit as h goes to 0 of this difference quotient, then we have the instantaneous rate of change. This one would be at 175. This would be the slope of the tangent line, and that slope of that tangent line would give us the instantaneous rate of change. So we are now ready to define the derivative, one of the fundamental ideas from calculus, and that is going to be this limit as h goes to 0 of f of a plus h minus f of a over h. So the slope of the tangent to the curve at a, and our notation is this is read f prime of a, and this means the derivative at a. So the slope of the tangent to the curve when x equals a. We also could write f prime of x, and this would be the derivative of a function with x, and we would say the limit as the change in x approaches 0 of the change in y over the change in x. So this is just simply a slope, and then letting the difference between the x's approach 0, taking this limit, and that would then be called the derivative, and the notation is f prime of x. So the derivative f prime of a is the instantaneous rate of change of y equals f of x with respect to x when x equals a. That's just simply stating then derivative is the instantaneous rate of change at a given point. This last screen will just be a lot of different ways to state this idea of the derivative. The slope of y equals f of x at x equal a, so the slope of this curve at a is the derivative. The slope of the tangent to the curve at x equal a, if we looked at that tangent line itself and its slope, which would be the same as the slope of the curve, that's another way to state this idea of the derivative. The rate of change of f of x with respect to x at x equal a, the derivative of f at x equal a, the limit of the difference quotient as h goes to 0, and all of these give this same concept, and this is one of the main ideas in calculus, the idea of an instantaneous rate of change at a, or a derivative.